Okay, so let's start. Okay, so let me recall from the previous lecture the following definition. So G will be a truth with some base in S, and introduce the following definition. It's like that number is the present version of manual. So let's explore that one. So what that is the very simple of multiplication time and certainly avoid here that one of the tests. Every on 12 of the office, or from the page to the one, with page. Okay, so there is the largest subgroup of multiplicative type, which is sample, and which remains so the elevated function. Okay, so just one remark that well, so one let's be a discrete valuation ring with spectrum field uniformly parameter.
Then one knows that over the spectrum of our discrete valuation ring, there exists a group scheme G such that, so if I picture the S as, so we have the generic point and the close point. So this is a spec K, so this is a spec okay, so the whole thing is S. So so there is an example such the fiber here is a GMK, and the special fiber is GAK. Okay, and so this group G, so G has, so G is commutative. So it is commutative. But G has, and So you see that because of this fiber here, which is the additive group, so the trivial group, let me denote by E, is a unique empty subgroup of G, and hence G has no reductive center. Because well, because under the base change, if we restrict to the generic fiber, so GK is GNK. Okay, so well, so you see that if the reductive rank of the fibers vary, well, if the reductive rank is not a locally constant function on the base, you cannot have a reductive center. So the existence of a reductive center is tailored to be a good notion for reductive groups, or at least groups where the reductive rank is a locally constant function on the base. Okay, so this is the first point. And I want to prove a theorem. So I will need the following proposition. 28. Okay, so assume we have an exact sequence of S group schemes. So K lying inside H and going to Q, going to 1 with H commutative and the kernel of K and Q of multiplicative type. And then H itself, then H is multiplicative type. Okay, so I will not prove this. So I just give a reference or proof. So this is, this can be found in LTA 3, chapter 17, and this is proposition 7.11. And it's also in the book by Demazure and Gabriel. And there it is, chapter 4, paragraph 1.4, proposition 4.5. Okay, so this is a technical result that we will need. And now we have there is a theorem about a reductive center that I will write here. I will erase the example. So we have the following theorem. Okay, so let me repeat the assumptions that G is a smooth, affine group scheme over S. And there is the first assertion that we proved already the other day. It is that if G has a reductive center locally for the FPQC topology, it has a reductive center. So this means that if after some FPQC, if over some S prime, which is FPQC over S, we can construct a reductive center, then it descends to S. Okay, so this was proved already the other day. And so there is a variant of A, which I do not repeat, which is contained in A, and that was proved also the other day. Now we have this fact that if Z is a reductive center for G, then the quotient G over Z is a group scheme, is a smooth, affine group scheme. And its reductive center is the unit. Okay, so and now we have assertion D. So suppose G has connected fibers and a maximal torus T. Then we have two assertions. So D1 that if H is an empty group over S, then any central morphism from H to G factors through T. And secondly, let G be the Lie algebra of G. And let theta be the restriction of the adjoint representation to the maximal torus T. So this is a group homomorphism from T to GL of G. And then the statement is that the kernel of T is a reductive center. Is a reductive center of G. Okay, so under the assumption that G has connected fiber and a maximal torus. Yeah, kernel theta, thank you. Okay, so we just pick any maximal. So if we have one maximal torus, so the kernel of the adjoint representation is a reductive center. Okay. And there is a last statement in the theorem that if S is the spectrum of a field. Um, with K an infinite field. Well, okay, I will write. I will write this later when there is one. So when we have proved all of this, I will erase this and prove the assertion of our field. Okay, so let's prove all of these properties. And well, so I remind you that the ultimate goal of this lecture is to prove that of a field, an infinite field, a smooth affine group scheme contains a maximal torus. So the proof is very Grothendieck'ian. So the proof is long, and every step looks very natural. So you see step by step, you see, well, okay. At the end, the proof is done, and the audience may well. So de Mazure told me several times that when Grothendieck were lecturing to them, sometimes they were getting bored or lost because everything looked so easy and so natural. They were wondering, but where does he want to go? And at the end, something was proven. They didn't, well, they didn't really understand where were the crucial points. So to avoid this pain to you, I will try to add some intermediate results after the various results, just to explain to you where we are heading to. And don't hesitate to stop me and ask, why are you doing this? Where are you going to? Because, okay, so let us prove this, and then I'll give an example. Well, then I'll explain why all these statements are important. Okay, so let's prove C. And so let Z be the reductive center of G. So in particular, it's a group of multiplicative type. And so this implies, but what we saw in the previous lecture about multiplicative group, that the quotient G over Z, so the functor, this functor is represented by a scheme of S, and indeed a group scheme because Z is central and it's particular normal. So this is a group scheme. And for a general N, which is smooth, which is okay. So why is it smooth? Because we have a G, we have the, so let's call this G prime the quotient. Okay, so they both lie over. And so by assumption, this is smooth. And so this is, so this one is faithfully flat. And enough finite presentation. And well, so this one is also smooth and basically flat, finitely presented. So this one is also faithfully flat and a finite presentation. So smoothness can be checked on the fibers and fibers. So the fibers, so they are GS over ZS, they are smooth, because it's a result that it's a result that over a base field, a quotient of a smooth group scheme by any subgroup scheme is if the big group is smooth, then the quotient is smooth too. Okay, so G prime is smooth. Okay, and so the fibers are connected again because the fibers of G are connected. So G prime is smooth with connected fibers. So, okay. And let Z prime be a central multiplicative type subgroup of G prime. And so what we want to prove, so we want to prove that Z prime is a unit group. Okay, but so it suffices to do this fiber-wise. So we are reduced, so we can assume that S is a spectrum of an algebraically closed field. Okay, because so okay, so so we are now in this setting, and so let Z1 be okay. So let us call pi a projection from G to G prime, so which is this quotient Z over Z, and let Z1 be the inverse image of Z prime. Okay, and so we have, so by definition, we have an exact sequence. So we have an exact sequence like that. And we know, and so by assumption, Z and Z prime are groups of multiplicative type. This is the assumption on Z prime, and it was also the assumption on Z. And so what we want to do, we want to prove that Z1 is central in G. And so we consider the action of Z1 on G by conjugation. Okay, so we want to consider expressions like that. And since Z is central, this induces so this action factors through Z prime. So Z prime is Z1 over Z. So we have an action of Z prime on G by conjugation, and since Z prime by assumption is central in G prime, so we have that the projection of Z prime G, Z prime inverse. So this is I of G. Okay, and so this give, so this imply so this implies that for every S scheme S prime and points, so Z prime in Z prime of S prime and G in G of S prime. This means we have so the action of Z prime on G, so which is Z prime G Z prime inverse. So this means that this is equal to G times some element which depends on Z prime and the projection pi of G. And so this is an element in Z of S prime. So this is a consequence of this fact. So this conjugated element has the same projection as G, and so this one and this one, they differ only by an element of Z. And since Z is, okay, so so we get a morphism. So we get a morphism of schemes. That's what I call B. So from Z prime cross G prime to Z. So which stands okay, so which stands and since Z is central in G, then an easy computation shows that B is B multiplicative. That is, if I take two elements here, so this is just the product 2, and it is also multiplicative in the second variable. Okay, so that is P is P multiplicative. And therefore, hence, it corresponds to a group morphism, to a morphism of S groups from G prime to as a functor of the functor of morphism of S group from Z prime to. Okay, but because giving a B multiplicative map like this is the same thing as giving a morphism of group, as I said. And now this one is connected. And it turns out that this one is étal. So this is an étal group scheme. This is an étal group scheme over S, because if U is an open subset of S such that over S Z corresponds to an finitely generated abelian group M, and Z prime corresponds to an abelian group M prime. Then we have seen in August that so let's give a name to this group. Let's call it E. This is a group functor. Then we have seen then that E restricted to U is a twisted constant group type the abelian group of homomorphism of groups from M to M prime. Okay, so these two groups are of multiplicative type over S. So over each point of S, the fiber is an empty type group which corresponds to some abelian group. And the function type of the fiber is locally constant on the base. So we can cover S by open subsets where Z and Z prime are of constant type. And then we know that this scheme is a twisted constant group corresponding to this group, and hence it's in particular étal. Okay, and now we have a map from a group with connected fibers into an étal group, and so this morphism has to be trivial. And so the conclusion is that U is trivial. U is trivial. So it is a constant morphism with value as a unit element. And so if we come back, this means also that B is a constant function with values the identity element. And And finally, this gives that Z1 is central. Okay, so let me finish the proof here. Okay, so we obtained that Z1 is central. Yeah, so this proves that this induced action by conjugation of Z prime is trivial. And so we do obtain that, hence Z1 is central in G. And in particular, it's a commutative group scheme. And now the proposition that is here, and then this proposition implies that Z1 is multiplicative type. And it is central in G. Hence, it is contained in the reductive center. And it contains the reductive center, so in fact, they are equal. But the point is that hence, Z prime is a unit, is a unit group. And so this completes the proof. This completes the proof of this. Okay, so if there is a reductive center, then we can mod it out, and then the quotient group has a trivial reductive center. Okay, and let us prove D now. Okay, so this, well, maybe this will be needed again, but okay, so let us prove the first proof of D1. Okay, so let H2 G consider a central homomorphism. A central homomorphism. And then the assumption is that we have a maximal torus, and we know that the group functor, the centralizer in G of the torus is representable. So it is represented by a smooth closed subgroup scheme. So let's call it C or C of T if one wants. And so since it is closed inside G, it is affine. And we also know by a general result that the Lie algebra well, okay, no, okay. And okay, and so we know, okay, then T is a group of multiplicative type because it's a torus and it is central in C. And we can form the quotient U equals C over T. And this exists, and this is an affine group scheme. And now we have this morphism U, which is central. And since it is central, U factors through C, which is the centralizer of T, and we consider, so let's consider the composed morphism. So we have U, which goes so we have U which goes to G, but since the image is a central subgroups, it commutes with T, so U factors through the centralizer, and we can follow this by the projection, and so we end up in U. And so let's call V this composition, and we are going to prove. So we are going to prove that we're going to prove that V is trivial. So we are going to prove that the kernel of V is actually H itself. And actually, so if we prove this, then we are done, because if V is the trivial morphism, this means that U factors through the kernel of pi, which is T. So hence we will have that U of H is contained in T, which is what we want. Okay, so we have to prove this. But if we call K, if we denote by K is a kernel of V, so it is a closed subgroup of H, and as such, it is and it is also a subgroup of multiplicative type, and it's enough to prove that K is equal to H fiberwise. Okay, because it's always the same argument. So both correspond to some abelian group, and it suffices. So if the inclusion is inequality on some fibers, I have the same type, and actually they are equal. Okay, so again we are reduced to the case of a base field. So we can assume that S is a spectrum of a field which is algebraically closed. Okay, so in this case, U is unipotent. So in fact, so of an algebraically field, so we have this group which contains a maximal central torus. So the group is nilpotent, and it's a direct product of a torus and a unipotent group. And every morphism from H, which is multiplicative type, U is trivial. Okay, hence, hence we obtain that K is equal to H. Okay, so we have, so this is done. So, and now let's prove D2. Let us prove of D2. So set letters denoted by Z the kernel of theta. So it is a closed subgroup of T, so it is a group of multiplicative type. Okay, so let us prove that Z is a reductive center. A center of G. Okay, so we start again with a morphism U. So let me continue the proof here. So now this. Okay, so again, let's consider a morphism axis central with R. Okay, well. Well, okay, so let's, so we consider some S-scheme S prime, and we consider H of multiplicative type over S prime. And let U be central. Okay, so we want to prove that U factors through Z S prime, but Z S prime is nothing but the kernel of the map from TS prime to the base change. So we can simplify notation, so can assume so it's enough. Okay, so we can simplify notation. And set S prime is equal to S. So that this means I don't want to want S prime everywhere, but so what I want to prove is that doesn't change if I go to S prime. So we have to prove that H factors through the kernel of the adjoint representation. Okay, but since U is central, so the action uh, since U is central, so this composite, so this composition here is trivial because well, so the adjoint representation is a derivative of the action by conjugation, and since U is central, the conjugation action is trivial. Okay, so so U factors. Yeah, exactly. So U factors through the kernel of the adjoint representation and T. And so this is precisely the kernel of theta. So it satisfies the universal property. It is a, so the only point that remains, it just remains to see. It remains to see that Z is central. So this we have not proved yet. But this is going to be quick. Prove we want to prove that the centralizer in G of Z is G. But we know that both, so this one is smooth. And so this is a subgroup, but we know that the Lie algebra of the centralizer so it's one of the general facts that I think I've written before. The Lie algebra of the centralizer is equal to the fixed point of Z in the Lie algebra of the big group. But since Z is the kernel of the adjoint action, so this is E of G. And hence, we do have what we want. And the centralizer is equal to G. Okay, because it is a cross subgroup, and on each fiber, well, the fibers of G are connected. It's a smooth connected group, and we have a subgroup with so we are done. Okay, and so we have proved this, and I will now write just the last statement of the theorem. And then I give you I give you a consequence of the theorem, and then you will understand why this theorem is important. And the assertion E is that if S is a spectrum of a field, okay, a field, then G has a reductive center, Z, and further, we have a bijection between the maximal tori of G. So this is in bijection with the maximal tori of the quotient group G prime, which is G over Z. Okay, so this is the last statement. Okay. So let's prove the first assertion. So just to be clear, so let's call this E1 and let's call this E2. E2. And I will prove only E2, E1 for the moment. So proof of E1. Well, since we are over a field, so over a field, the centralizer of a subgroup is always representable, and so the centralizer, so the center of G, so which is a centralizer in G of G itself, is represented by a closed subgroup. Let us call it H. Not necessarily smooth, not necessarily smooth, but never mind. Okay, so let me continue here. Okay, and okay, so H is okay, and we know. Okay, so C is a book by Demazure and Gabriel. So since we have taken the center, so since is commutative affine K group scheme, that H contains largest multiplicative empty type subgroup Z. So we have a candidate for being the, and then one proves Z is reductive. Okay, so the proof is not difficult. I will not give it. Well, but it's plausible that it is because, well, it is the largest one over K, and one can prove without difficulty that it remains so after every base change. And then this is a standard proof. If you have a maximal torus, it contains the reductive center, and so the image in the quotient is a maximal torus. And conversely, if you take a maximal torus here, the inverse image is a, okay, so we have all those things. And let me conclude this lecture with, well, maybe not conclude, but let's give the following corollary. let G smooth. It, well, I mean, a smooth affine algebraic group of a field K, and let capital K be an algebraically closed field containing the given field K, and suppose that the group GK is nilpotent. Then G has a maximal torus. And so the proof is easy. So proof so by hypothesis, so the group G prime equals GK, so it is nilpotent as a unique maximal torus T. And T is central. So let's call it T prime. Okay, and so by part E of the theorem, which I have not proved, but which is standard, so T prime is a reductive center. Is a reductive center of G prime. And so by point A of the theorem, T primes come from a closed subgroup E of G, which is a maximal torus of G. Okay, so in the nilpotent case, what we did is enough to guarantee the existence of okay. So maybe I take 5 more minutes just to give the definition that I'm going to use in the next lecture. And okay, so let's erase this theorem. And is it okay if I go until 4:45? Okay, so the next paragraph is about Cartan subalgebras. So in this paragraph, K is an infinite field. Capital K is an algebraically closed field such that K is contained in capital K, and G is a finite dimensional Lie algebra. We introduce the following definition. So we consider an element X in our Lie algebra. And we define its nil space. So the nil space of X in G. So it is a union for all integers I and star of the kernel of add X to the power E. Well, of course, add X is a map from G to G, sending Y to X bracket Y. Okay, so the nil space is just a generalized eigenspace for the eigenvalue 0 of this linear operator. And we introduce a number. So we define the nilpotent rank. So rank, the nilpotent rank of G. So by definition, this is the smallest possible dimension of this nil space. Okay, so I just want to say that the set of, and we say that an element X in G is regular if the dimension of the nil space is minimal. So if this is equal to the nilpotent rank of G. And so we have the lemma. So the set of regular element is an open dense subset of G. So this is more or less straightforward. So we consider the function. So let T be an indeterminate. And for all X in J, we can consider the characteristic polynomial, that is the determinant of T minus add X. And so let's call D the dimension of G. So this is a polynomial in T. So this is T to the D plus C1 of X, T to the D minus 1 plus so the general term is C to the I times Ci of X times D minus I. And so okay. So if we call R the nilpotent, okay. So this means that this is so this is the largest R such that T to the R divides this polynomial, and so all such expressions. So clearly we are taking a determinant, so they are polynomial functions on G, and hence, and it is here that we use the hypothesis that K is infinite. They they uniquely determine elements, so that they are actually polynomials on this. Oh, sorry. So there is no more. So each coefficient is and R is the greatest. R is the smallest index I such that the correct polynomial is not identically 0. And so the set of regular elements is the open subset given by the non-vanishing of this polynomial. Okay, so we do have, okay, and one last definition. So if X is regular, then, okay. I think it's the smallest because yeah. And so let me just to give the name. So that's proposition of definition. If X is regular, then the nil space is nilpotent Lie subalgebra of G, which furthermore equal to its, so let's denote it by H, equal to its own normalizer. That it means that H coincides with the set of X in J, no, of Y in J such that add Y of H is contained in H. And it is called a Cartan subalgebra. Of G. Okay, so this will be the topic of the next talk. So I have defined Cartan subalgebras. They exist because there are regular elements, and we will nearly prove that every Cartan subalgebra comes with some subgroup, which turn out to be a maximal torus if the group is reductive. So just so Grothendieck calls this a Cartan subalgebra in SDA3, but the name Cartan subalgebra was already introduced by Élie Cartan to denote a nilpotent subalgebra equal to its own normalizer. And so this is somehow more precise because Grothendieck requires it to be equal to some nil space. And so for this reason, we call this a G Cartan, where G stands for Grothendieck. So it's not clear for an arbitrarily Lie algebra that every Cartan subalgebra is G Cartan. But Grothendieck proves that this is indeed true if G is a Lie algebra of a smooth algebraic group. So, so in the case of interest, the two notions coincide. But just to be on the safe side, let us call this a Grothendieck-Cartan subalgebra. Okay, so next lecture will prove that, well, up to minor twist, if G is reductive, a Cartan subalgebra is a Lie algebra for maximal torus, and so for maximal tori exists. Okay, thank you.